in our lab is giving this data to people on the airfield who need the information. They need to know what species of birds they're having problems with right now, not 2 years ago and not 2 years in the future. They need to know right now so they can go out there and do some kind of habitat management or implement some kind of pest management program that will help reduce birds from wanting to come into the airfield. We have some tools that we have in our lab to help us identify bird strikes. We have a microscopic collection of feathers, and we have a microscope that has a stage for an unknown sample and a stage for our known collection. We have a bird collection of specimens that we use to match feathers with this. We have a library with field guides telling us distributions of birds and all kinds of information on bird habits. And then we have a DNA facility where we can actually use some of the material that we have been collecting over the years, the tissue samples that we've been collecting, to build a known reference, a library reference of DNA sequences that we can use to identify bird remains. So these are some of the samples that we may get, ranging anywhere from a piece of blood or tissue all the way up to, we used to get whole carcasses, and then we got in trouble with the mailroom because they were a bit smelly. So now we ask them not to send the whole carcass anymore. We ask them to pull feathers and send feathers in a plastic bag. We wash them if they're dirty, get them back into their natural shape and color, and then we will take the whole feather out into the collection and match it up with a museum specimen for a perfect match. That's simple and easy and the most straightforward way to identify bird strikes. Some of your airport people can probably do that just because you know what's on the airfield and you know what these feathers look like. We have a collection of about 620,000 museum specimens. This is one of the largest collections in the world. This is one aisle. I think we have 13 aisles. So this is very, very valuable for identifying bird remains. And if any of you ever get up to Washington, come see us. We will bring you behind the scenes and show you a bit of our collections. We have about 85% of the diversity of birds of the world represented in that collection, so that's why it's an ideal place to do this kind of work. If we don't have a whole feather or carcass or something that we can visually identify, we will look at the whatever material we have sent to us, and sometimes it's a paper towel with bird material, snarge kind of material that's just bird ick, wiped off the aircraft and sent in a paper towel. It could have a little bit of feather attached to it, or it could just be a cotton swab that someone's wiped off. This is the kind of material that doesn't have any feathers in it, really. I mean, it may have some downy barbules in there, but there's really no whole feathers in there. So we had to come up with another way to do this. And what we use now is DNA barcoding. And if you think about a barcode in the supermarket, it's a bunch of lines with zeros and ones that you see on the label, and that will tell you how much the product costs and where it's located and what it is. Well, if you look at the DNA and you see the A, C, T's, and G's, they form these little peaks when you do the sequence, and if you squish those all together, it just looks like a barcode. And that's why they came up with the term DNA barcoding. It's actually a small snippet of mitochondrial DNA, about 650 base pairs of the CO1 gene. We will run that sequence, get our 650 base pairs from the piece of blood or tissue that we have extracted, and put it into the Barcode of Life data system. This is an online, publicly available database that anybody can use. And it not only has birds, it has all kinds of animals, plants, fish, and the goal here is to sequence everything on Earth at some point. So we will copy and paste the sequence into the Barcode of Life database, and immediately spits out the answer, the most similar answer to our sequence in the database. In this case, it was a wood duck. And it shows us that we have how many individuals are in the database, and it also shows us the next closest taxa. So we can make a determination based on the similarity indexes of these DNA sequences as to what the bird was that hit the airplane. Now you have to really still have to use your mind, even though we have these wonderful molecules. And sometimes you still have to use your morphological knowledge. So we had this case a while back from Randolph Air Force Base in Texas. And it came in on this piece of cheesecloth that was blood. And we took a small snippet and we sent it to the DNA lab. And we sent it 3 times, and it kept coming back as white-tailed deer. Well, that's okay, because I showed you zebras have been hit, and I told you that mammals get hit. The only problem, this was 1,500 feet above the ground. So we started to wonder what was going on here. We looked at the date, and we said, oh, it's after Christmas. It must be Santa. But we called the pilot and we asked him, are you sure that there's not some misinformation here? Maybe you were on the ground when you hit this. And he said, no, no, no. You know, it did $8,000 worth of damage to my aircraft. It hit the wing of the aircraft, so I know that I have the information is correct. So now we have to explain what went on here. So I went back to the sample and I made a little microslide of the material, and sure enough, wrapped around some of the blood in that sample, I found a small feather barbule attached to some of the blood. Now we did find deer hair in the sample also. But what happened was we matched it up with the microscopic characters of a bird in there, and the bird was a black vulture. So I think we solved this one. I think the black vulture was feeding on the deer carcass and actually had some deer remains in the crop and took off when the airplane scared it up, and it hit the vulture, and the crop material is what we were getting with the DNA sample. At least we know Santa came back, so I think that's what happened. I wanted to go over the event that we worked on with the Flight 1549, just to show you how detailed some of these investigations can be. Most of the time we get a single bag of remains, and we will work on the identification and give an identification. But in this case, we had a lot of material because it was a very high profile and very serious event. The pilot knew that it was birds. The aircraft sunk into the bottom of the Hudson River. The engines were on the bottom, one for 3 days, and one I think was down there for like 10 days. And so every time they went in to work some more on the investigation and tear down the engine, they were sending us more samples each day. So in this event, they had to describe exactly what happened all the way back through the engines, any possibility of any kind of bird remains or where things were going to be found. We had to help them out with that. And so the investigation took a long time. We received 69 samples total, and we received some whole feathers and some microscopic feathers, and then we did a lot of DNA extractions. We did the extractions in 2 different labs, and we did a lot of verification of each sample because we wanted to make sure we were right on this one. And this is some of the actual evidence. This is a, you know, whenever you get bird remains from an accident, you're going to have a lot of a mess in there and not a nice clean sample like some of the known slides that I showed you before. We did get some whole feathers. The question here was whether or not this was a Canada goose or a brant goose, which is a very similar looking species that occurs in New York and is actually known to be increasing in populations. And the big question here is, I don't know if you remember, but I told you our engines now are designed to take 4-pound birds. The weight of the brant goose is 3 pounds, and the Canada goose is 8 to 10 pounds. And so the GE engineers were very nervous that maybe it would be a smaller bird than what their engine was supposed to take. It did turn out to be a Canada goose. And then we decided to do a little bit more with this and try to determine whether or not the birds that were ingested in this event were migratory birds from New York, resident birds from the airfield on New York, or migratory birds that were down in New York for the winter. And so we looked at those whole feathers that we pulled out of the engine, and we did some stable hydrogen isotope analysis. And all that is just extracting the elements from the feathers to determine what those birds were eating and feeding on. And what this does is the country is divided into these gradations based on these element numbers. And so we took the feathers from the engine and we extracted the isotopes from those. We got the biologists on the airfield to capture some of the resident birds there that they had marked, and they pulled some feathers from those birds. And then we took museum samples and we looked at the isotope values of birds that breed up north. So what happens with the Canada geese is they molt their feathers on their breeding grounds, and they're taking in the elements from the environment as they're growing their new feathers. So from our analysis, we were able to determine that the feathers from the engine had values that overlapped with these areas up here in Canada. And so we concluded that those birds were not the resident birds in New York. They were birds that were down in New York for the winter. They bred up in Canada summer before. So what that told us was that it's not the problem with the birds on the airfield right now, it's the problem with the migratory birds. And it made sense to us because those birds were hit at 3,000 feet at 5 miles off the airport. And so it would be very unusual for the resident fat Canada geese to be up flying that high whenever they can go out to the park and get popcorn and feed on local food. So it all kind of made sense. But this was a new technique and new information and technology that we were able to apply to this case to help us realize that now what we need to start thinking about for aircraft safety is the migration of birds and the migratory birds, and how can we see that, and how can we tell pilots where are these big migratory flocks. So that's what we're going to face in the future. Another big problem with future and bird strikes is that we have a lot more larger birds out there now than we had in the past. This is just some birds from North America, and the population status of these birds is increasing over the years, and all of these birds are birds that weigh more than 8 pounds, which is what I told you our standard engine design is now. Tundra swan is not even a native species, the mute swan is not even a native species in North America. It was introduced, and the populations of this bird have just been astronomically increasing over the last 30 years. And the same with the Canada goose, the white pelican, and the bald eagle. In fact, 13 of the 14 species of birds in North America that weigh more than 8 pounds have witnessed significant increases in their populations over the last 30 years. So we need to think about this seriously and tell people who are making decisions about this that we have to do something on our airfields to keep these birds away. Don't worry, Colombia is doing something. There was a summit in Bogota in June, and there are people who are aware of this problem. I don't want you to be afraid to fly. There are people who are working on for your safety, and we just need to help them and support them, and let them know that we appreciate what they're doing to keep birds away from airfields. But as a result of this summit, some organizations, including the Federal Aviation Administration and the U.S. Department of Agriculture, is going to be collaborating with some airfields. They are doing a pilot study now, starting in Panama and Ecuador, because they have deemed those airfields to be the most serious risks right now. After this pilot study, they will be expanding this program to more countries in South America to provide more training and more education, and hopefully make our airfields a safer place. Okay, we do more than bird strikes. Bird strikes is our big issue, but feather identification is used in a lot of different fields. We use it in anthropology, particularly to identify feathers on anthropological items. This might help us learn something about the culture of people that use these items. But also, when we're sending things across the border, this was a mask that was being repatriated back to Canada, and we needed to know the species of birds on the mask so that we could ask for the proper permits to export this item. It turned out these were dyed chicken feathers, and chickens are not protected, so this item didn't need any permits. This one, on the other hand, was an anthropological item used by Native Americans, and we identified some of the hawks and eagles and different birds on there to help the researchers study that item. Up in the Yukon, they are starting to find anthropological artifacts that are melting in ice patches. And they're pulling things out of here that have whole feathers and whole feather pieces and bird pieces. And we've been working on identification of those items, too. Some of those things are 8,000, 10,000 years old, and they still have really nicely preserved feathers. I think it's because they were in the ice for all those years. The U.S. Fish and Wildlife often has cases that involve personal property. Someone owned this item, and it was reported, so it was confiscated and brought to the museum for identification. We do have a lab specially designed to do this kind of work. It's out in Ashland, Oregon, and it's the Forensics Fish and Wildlife Lab. But this case was brought to us for identification. So they thought here was that this was an eagle headdress. We did some samples, some microscopic samples of this, and realized that it was actually dyed turkey